Alright, so here we have a sequence, and we want to know if it converges or diverges. Whenever you see this term here, this tells you that you have an alternating series. This -1 to the power of anything. Wherever you see an alternating series, you know that the only thing you can do is the alternating series test. Now, the alternating series test has 3 conditions. Condition 1, a of n, or the absolute value of a of n, must be, right, this is the most technical way of saying it, monotonically decreasing. Okay, what does that even mean? That's some weird mumbo jumbo. In other words, a simpler way of showing it is that a of n must be less than or equal to a of n plus 1. Okay, that means every term should be decreasing. So every term must get smaller than the previous term. Now, why do I put the absolute value? Okay, the absolute value is required because the alternating series test does not consider the actual series. It considers the absolute value, right? If we had a of n, then we would want to consider the absolute value of a of n, okay? It's easier to predict how the absolute value of a sequence behaves as opposed to the non-absolute value, right? Because we have some terms that have that negative, some terms do not. So we sort of get rid of that -1 term by taking the absolute value. So basically we consider this part here, right? That's the only part we consider. So where do we go from here? First, to prove this, there's one of 2 ways, okay? Either one, you take the derivative, okay? Derivative, or you just show. The show one is very simple, but it's not always true, which is why it's a bit of a weak argument. For calculus 2, it's possible, or sufficient, actually. That's better to say. All right, so let's do that. Let's show it. The derivative, all you must do is say that f at n is that absolute value. So it'd be n squared over n cubed plus 1. And then you show that f prime at n, right, or the derivative, is less than 0 or equal to, so it's negative for all n, all right? And this will be all integers, right? Because we want to show that the change is always decreasing or the change is negative, right? Now, for show, you literally just show a of n. So we say, like, for example, a of n would be the following: n squared over n cubed plus 1. A of n plus 1 would be n plus 1 squared over n plus 1. Now here, because we're adding one, or a few terms really, but because our actual term here is a bit more, we can sort of say, or sorry, smaller. Let's expand this out to explicitly show n squared plus 2n plus 1 over, okay, n plus 1 times n squared plus 2n plus 1 plus 1. Okay, now immediately here, we see that this top term is bigger by 2n plus 1, not there, and that this bottom term is greater by this much. And because the top term got bigger and so did the bottom term, we should have overall a smaller fraction. Thus we sort of, did you get that? Okay, so look, thus we get a overall, thus we get an overall smaller term, okay? So it's sort of implicitly shown. But of course, this isn't always true, because at some point, things just might go like this. We passed our first test. Now, the second condition to pass the AST is the following. But we need to have that, the limit, right? So, the limit as n approaches infinity of the absolute value of a of n must equal to 0. Otherwise, it will not pass the test. So, let's test it out here. We would have the limit as n approaches infinity of the absolute value. We're going to just write here n squared over n cubed plus 1. And we know this will go to 0 because the degree on the top is less than that of the degree on the bottom. Alright? Thus you will have n cubed overpowering n squared. Okay, because this is similar function to n squared over n cubed, which is the same as 1 over n, and we know this converges to 0. Alright, thus we pass both of these tests, and thus we have this function, or this sequence, converging, right? However, to find what value it converges to, that's a different story, but all we needed to know is whether it converges or not. Hopefully that helps.